Dr. Luc van den Hove is the president and CEO of Imec, and he is with me to give us an inside look at the technologies driving the next generation of computing and the breakthroughs that could define the future of AI. Dr. Luc van den Hove, such a pleasure to have you on Connected on TaiwanPlus.
Nice to meet you.
I'm going to start with something you have said that has really not only intrigued me, but many in this space in Taiwan. You've said that we're approaching the wall of physical boundaries in Moore's law just as AI demand explodes. So in that context, what does scaling mean?
Well, I believe that the demand for more advanced compute power is kind of exploding. The way AI is evolving actually requires an exponential increase in compute power to address all these needs. This, we believe, will kind of be a very strong driver to continue to develop more energy efficient technologies. Because if you don't do that, the energy consumption of those data centers will just explode in an exponential way. So we have to come up with more energy efficient computation. And one component, one element to enable this is to continue Moore's law. But this is getting harder and harder. The transition from one node to the next one, just based on pure geometry-based scaling, is getting difficult. Now, I'm still convinced that it is the way to get the most efficient scaling, because lithography-based scaling basically enables a exponential scaling effect, but it's getting harder, and therefore we may see some slowdown in node transition, and that we believe is going to be compensated by leveraging the third dimension in various forms and shapes.
And we're going to talk about some of those that Imec is working on, but before we get to that, you've also warned of a time, which perhaps is happening right now, when hardware lags software. What kind of an issue is that going to cause for companies that are operating right now and the industry?
Well, it is indeed true that kind of model development in AI goes extremely fast. And we believe that that's not going to slow down, especially also with the transition that is imminent of large language models towards agentic AI, towards physical AI. We will need a much broader variety of models to address various kinds of workloads. And so that changes extremely quickly. Kind of new models come out every couple of months. The problem is if you have to develop kind of a dedicated chip, a most power optimized chip for each of those models, well, designing a chip takes 2 years, I would say. So we have to kind of rethink this concept to some extent and probably come up with chip platforms that can serve multiple models and think about some kind of new reconfigurable architectures, and we're working on some of these concepts.
One of the things that Imec has been working on and talking about is 3D stacking. Mm-hmm. It's touted as a key breakthrough. Can you tell us how it's transforming performance and energy efficiency?
Mm-hmm. Well, we're strong believers in 2D scaling. So lithography-based scaling is absolutely still the most efficient way to scale. But as it gets harder and harder, as we're kind of approaching those limits where the improvement node by node is somewhat slowing down, we have to compensate this by other techniques. And so 3D, leveraging the third dimension is going to be absolutely important. And we can do that in many ways. We can kind of start stacking transistors on top of each other and at the transistor level. That's what we call our CFET approach, complementary FET approach. And we believe that we may introduce this at the sub 1 nanometer generation, like maybe the A7 node. So that's one way. But the second way to leverage the third dimension is by stacking chips on top of each other. We believe that provides quite some advantages. Just one example to illustrate, in AI, one of the big bottlenecks is to a lot of data, a lot of time and energy is lost by moving data from the memory to the processor. And if we can bring the memory closer to the processor, we can save quite a bit of energy.
Does it matter what the size of those chips are when you're stacking?
Sure. Yeah, you will have to really optimize the size of the chips to match the various chips on top of each other, depending on kind of the stacking technique that is used, whether it's a die-to-wafer stacking or hybrid bonding, where you have wafer-to-wafer bonding. So there are various ways to do it, but it's indeed going to be important to kind of optimize the entire architecture and make sure we use that real estate in the most efficient way. And that actually will also result in kind of a paradigm shift on how we design those circuits. Today, we're used to design our circuits in a 2D plane. And so one way to do that would be to design this circuit in a 2D plane and then start disaggregating the circuit and then move it on top of each other. But I believe in the future, we will have to go kind of a paradigm shift to really design the entire system truly in 3D.
But some argue that it may not be as sustainable for AI because it concentrates heat and the power density needed, and it may be causing more problems than it solves.
Yeah. No, I think this is a very important aspect. So management of power and management of thermals in these special 3D stacks. So that has to be taken into account also when you design those circuits. That's why we need true 3D design in order to optimize these systems on chip in a 3D fashion, taking into account the heat load, the hot spots, and we'll have to implement also techniques to eliminate these problems, like heat spreading techniques, new cooling techniques. So we'll have to kind of optimize the entire system.
I understand it is something that Imec is working
Absolutely.
on, these cooling techniques.
Yeah.
How much progress has been made on that, and is there a plan B if the cooling techniques that do come up are not adequate to what's needed?
Yeah, I think it's more than just the cooling techniques. It's a combination of various solutions that we have to combine. It's kind of heat spreading techniques. It is also optimizing your design so that you take into account the thermals during the design process. Integrate also maybe more sensors to measure the temperature of the circuit so that you can throttle the circuit when it gets too hot at certain places. And then indeed cooling techniques. But there's a wide variety of cooling techniques that we are investigating, including also direct liquid cooling using jet impingement techniques to get the maximum heat extraction.
Is it being used at all anywhere yet, or even in the pilot phase of products?
Well, there are first products that are coming out where like SRAMs are being placed on top of processors. That's the first step, but that's not yet kind of true integrated 3D design, I would say. These are kind of layers that are put on top of each other, each layer being designed individually, but those are the first steps. The next step that is being considered, of course, is to leverage the backside of the wafer using power distribution systems on the backside of the wafer. You can see that also as a first implementation of a two-layered approach. So we don't believe that this is going to be like a radical change immediately to the most complex implementation, but it will be a stepwise implementation, and so the industry will also learn from each of those steps. So it's a gradual implementation that we expect.
There's also an argument that each additional layer of 3D stack compounds the risk of defects, and even a small defect in one layer can compromise the entire stack.
Yeah.
And as far as yield management goes, that makes it extremely challenging. It could be very expensive, and for those that are put off by that, is there something to mitigate that risk? Yeah.
No, I think this is also a very important aspect, but you have to consider the yield is also proportionate or inversely proportionate to the size of the chip. So if you put everything on one chip, your yield will also go down if the chip gets too big. So if you disaggregate your circuit and build it out of smaller devices that you stack on top of each other, it may actually result in a yield improvement, provided you don't lose the yield during the bonding process. That's why there is so much innovation needed on the hybrid bonding techniques. Making that defect-free is going to be very critical to make this integration, 3D integration, a success.
As AI models evolve faster than design cycles, is there a risk that where a 3D stacking would lock in a design and then that could be quickly outdated and not be able to catch up with the evolution of AI?
Well, we believe that this 3D stacking will also offer opportunities to basically think of architectures, because we now have much more freedom how to build the architecture. Think of architectures that in the end may be kind of reconfigurable, software definable architectures. If we go back in history, FPGAs were kind of this concept, but with this 3D stacking, I think we can think of kind of a revival of some of these concepts in a more effective way. And so it can offer new opportunities, this through 3D design, to enable really dramatic changes in the architecture, actually, and make them maybe more reconfigurable, which could be a nice answer to this need for flexibility.
What is the biggest challenge to the semiconductor industry at the moment? Is it the evolution of AI, or is there something else that's likely, and I'm talking about in the technology space, to pose a challenge to the semiconductor industry?
No, I wouldn't say that the evolution of AI is a challenge. I would say it's a fantastic opportunity for the semiconductor industry. It's an enormous growth engine. I think if we look at the challenges, I think the challenge is that in order to address this phenomenal requirement of massive increase in compute power, the pressure on developing energy efficient computation becomes so high that the pressure on innovation is so high, and that will require actually to bring the best of the best together across the world. And that's why we are strong believers in collaboration, in connecting the strengths, because it's impossible for every region to be the best in everything. And if we want to enable this roadmap, we have to bring the best of the best together. And that's why I believe this connectivity and international collaboration is so crucial, so important.
And because we're at SEMICON, I do definitely want to talk about bringing the best of the best together. But before we move to that, I want to go back to the idea of companies right now and how they have to pivot or strategize or look at their business models and operational models. Do you believe that many chip makers risk becoming obsolete if they don't adopt Imec's strategy? And it's something that Imec has been, talking about and warning about a lot. The strategy of co-optimization, packaging innovation, and 3D stacking comes within that.
No, I think that it is extremely important. I mean, we come from an area where the roadmap was quite kind of obvious. We were just scaling, shrinking our transistors, putting more transistors on the chip, and kind of everything was rather predictable. These days, it's getting so hard to just continue the roadmap as it is. So we have to combine solutions from multiple disciplines, and that's why this notion of system technology co-optimization, software, hardware co-optimization becomes so important, because you have to understand the application, you have to understand the workload in order to understand what technology platforms are the best to address those workloads. So having that knowledge across the stack is so important. Does it mean that that every company has to do everything? No, I think that ecosystem developments are very important, and have very strong partnerships, as this country is known for. TSMC is so great in ecosystem development, building very strong partnerships with their customers, with their suppliers, and I think that's also what Imec stands for, is bring the entire ecosystem together with the goal to accelerate the innovation across the value chains, because we have to come up with solutions that take into account the application, the software, the architecture, the technology, but also the materials, because a lot of innovation comes from materials, and that's the role Imec is trying to play in this industry.
And speaking of innovation, and this is a question for one of our viewers, where do you see the boundary between pursuing further chip density scaling and investing in fundamental new computing paradigms like ternary or multi-valued logic?
I think that these new compute paradigms are going to be very important. We also are working on some new concepts leveraging like cryogenic electronics, superconducting materials, for example. People have been working for many years on that, but we believe that there are opportunities also to leverage some of the newest processing techniques to kind of scale down these concepts, and these could be interesting opportunities. Quantum computing is another domain that makes very strong progress and is going to leverage also kind of the way of working of the semiconductor industry, I believe, and so those are new compute paradigms that we will see on the horizon.
And speaking of breakthroughs and future technologies, Imec has been exploring 2D materials like graphene and novel compounds. Can you explain why you've been exploring that, and is that likely, or why there is a need to look beyond silicon?
Yeah. Well, if we want to extend the roadmap for the next 20 years, I would say, today the core transistor is built using these gate-all-around concepts like nanosheets. And in order to kind of scale it further down, in order to minimize short channel effects, we have to thin down the silicon in order to get better control over the voltage in the channel. Now the next step could be to make it ultra thin, use these kind of monolayer-like materials, 2D materials like molybdenum selenide or tungsten selenide, and we're working on those. We believe that we won't need these kind of materials for the next 5 generations, I would say, but our roadmap kind of envisages that today at 2 nanometer we start using nanosheets. We will be using that for like 3 generations. Then we will transition to what we call a CFET concept, where we put the N and the P transistor on top of each other, another 3 generations. So it's more like at an A3 or A2 node where we see the integration of these kind of new materials to replace the silicon channel by these new 2D materials.
Has Imec started piloting this or using this in any chip yet, or have we seen it in action?
Yeah, we're doing the fundamental material research on those materials, and we are right at the point where we're kind of transitioning these kind of materials from a lab to a fab concept, working with equipment suppliers to get those materials on like full 300 millimeter wafers with the required uniformity, required quality. This is the phase in which we are, but this is similar to like 20 years ago when we introduced high K materials and metal gates. It took about 10 years to really bring it into manufacturing. So we believe that these kind of materials, it's more than 10 years out from now.
And you've got an eye on a lot of the industries in different parts of the world. Can you see, or are you seeing more thinking towards this direction, new materials, kind of new innovative approaches, or do you feel like it's not happening fast enough?
I think the whole industry is about materials innovation, and material innovation is absolutely crucial. We will be using new materials in the front end, as we just discussed, these 2D materials, but also new materials for interconnects. We're also exploring a lot of new options to kind of replace the copper by, for example, ruthenium, and we're working also on various compound materials to improve the connectivity between those transistors. So new material research is absolutely crucial to make progress in this industry. And the same is true in the lithography domain, for example. A lot of innovation comes from new photoresist materials. We're now evolving towards metal-containing resists, dry deposited resists. So it's all about new materials, basically.
Speaking of lithography, I understand that Imec has just signed a 5-year partnership with ASML. Can you explain what that entails and why you found that necessary?
Well, we've been working with ASML for more than 30 years. Actually, it happened to be that Imec and ASML were founded in the same year, in '84, and we started to work together very soon after that. And this partnership has kind of grown quite significantly, become more strategic, and we kind of renew our partnership every 5 years, and we just did that. And that coincided with also a very strong investment from the European Commission in context of European Chips Act, where we're going to extend, which will enable basically a massive expansion of our pilot line. And this will be financed by European Commission, the Flemish government, but it will also be matched by industry, and ASML is a very important industry contributor to that. So we're going to install kind of the whole suite of new generation ASML machines, including the next generation high-NA UV machine.
You've always said IMEC's strength comes from the global ecosystem, but right now there's rising geopolitical friction. How essential is international collaboration? How essential are these partnerships that we're seeing over here at SEMICON to help the industry be sustainable and move forward?
I think it's absolutely essential. I think this industry really has thrived on international collaboration because it has become so difficult, and you have to connect the best of the best from all over the world. You can't be excellent in every aspect of this technology in every region. If every region would try to do everything on their own, it would be a major setback. It would lead to mediocrity. The challenges are so big. We have to bring together the best of the best wherever they are in the world, and that's why this collaboration is so important. Taiwan is super excellent on manufacturing and leading the technology. I mean, some of the best design companies, fabless companies, are in the US. In Europe, we have some top equipment suppliers, also in the US. We have Imec as the R&D source, and if we really want to move at the pace that is desired, we will have to connect these strengths. This is going to be absolutely needed. Otherwise, we will lose momentum in the industry.
Yet, many countries and governments are now framing their chip industries as a matter of sovereignty. So how is Imec balancing that and still ensuring that there is enough collaboration?
Yeah, no, it's a delicate balance we have to find, but I believe that the best way for a region to become relevant is to make sure that it strengthens its strengths and make sure that those strengths are kind of expanding across the value chain, and that we create reverse dependencies between the regions, and so that's the best way, we believe, to make the progress that is needed.
And looking ahead, what do you think is the most exciting opportunity in the future for the industry?
Well, on the one hand, I think, of course, AI is creating so many opportunities. So it's going to be an enormous driver to keep the momentum in the industry. At the same time, the use of AI and all of this technology into many new applications. Of course, automotive is kind of the imminent one, where we see it's kind of the first implementation of physical AI, but also in robotics, but then also in healthcare. I think we see so many new opportunities where chip technology and AI will bring disruptive innovations in healthcare, and I believe that that's going to be the next big thing also for this industry.
You've described supercomputers in cars using chiplet-based architecture for edge AI. What do you think are the unique challenges in power, packaging, and thermal management that automakers need to solve?
Well, we believe that chiplets are a very nice approach to integrate like this high-performance computer for a car, because the number of cars that are being sold every year, I think it's an order of magnitude lower than the number of phones that are being used. So it means that the volumes are somewhat smaller. And if we want to come up with kind of flexible compute architectures for various kind of brands or various kind of of levels of cars, then we need to have a flexible compute platform that we can adjust very easily to the requirements. And that's where chiplets, I think, can offer flexibility, can offer ways to reuse IP, reuse chips in different configurations. So that's why chiplets, I believe, are the way to go there. But we have to make sure that the quality, reliability is getting to the automotive standards, and also there is enough standardization specifically for the automotive applications. And so that's what our program is focusing on, to enable these chiplets for automotive.
And I know you've spoken about 3D stacking, materials. Is there something else that you're excited? Is there another breakthrough you have your eye on, say, in the coming 10 years as this industry evolves?
Certainly, in order to address these big AI challenges, one of the big challenges is indeed to connect all these chips and compute systems in the most effective way. And so photonics is really going to be the breakthrough technology that will enable this in various forms. To connect compute units using co-packaged optics, bring the fibers directly on the interposers. But the next thing is to also transition towards photonics-based interposers so that we can connect the chiplets in an optical way and combine many more of those to make these gigantic compute units that are needed for AI applications. And then leveraging those technologies towards new domains such as healthcare, where we can combine electronics, photonics, sensing, microfluidics in a very small form factor, we basically can build a full clinical lab on a chip. This can enable kind of new medical diagnostic techniques, but we're also working on platforms that will allow us to grow human tissue on the chip and then start to do bio-based testing of drugs as if we would be testing them in a human. And this is what we believe are going to be the platforms to generate lots of data that will feed like AI foundational models with real data, and so that AI models can be used for drug development in a more effective way. And so those, we believe, are some of the big next things that we're working on.
Luc van den Hove, President and CEO of Imec, thank you for giving us an exciting peek into the next level of technology. It's been great to have you on the program.
Great, you're welcome. Thank you.
Thank you.